Okay, so welcome. So we have Camille talking today, and he's going to telling us about measure equivalence, negative curvature, rigidity. All yours, Camille. Yeah.
Thank you. Thank you very much for the invitation here. And so indeed, I will give a mini course on measure equivalence in negative curvature. And today, the first lecture will be devoted to explaining you the basics on what measure equivalence is. So in a sense, measure equivalence has two sorts of motivations and origins. So there are some geometric motivations as it is a measurable analog of the notion of quasi-isometry, and it's related to the theory of lattices in locally compact groups. And there is another motivation coming from ergodic theory, and even in a sense from the theory of operator algebras and fundamental algebras, though I won't talk about operator algebras in the course. And so today I will present you the two kinds of motivations, geometric and ergodic. And I will start with the geometry. And let's start with let me start by recalling the notion of quasi-isometry between finitely generated groups and introduce measure equivalence as a measurable analog to it. So let me recall you that if gamma and lambda are two finitely generated groups, we say that gamma and lambda are quasi-isometric, which I often abbreviate as QI, if you can find lambda at least one and positive constant C, such that, so first, and there is a map from gamma to lambda, such that, so first you want F to be a quasi-isometric embedding, which means that if you take any two elements, gamma and gamma prime, in the group gamma, you want the distance between F of gamma and F of gamma prime. So this is the distance in lambda equipped with its world metric to be controlled from below and from above by the distance between gamma and gamma prime in gamma equipped again with its world metric up to multiplicative error and an additive error. Right, so this is saying that F is a quasi-isometric embedding from gamma to lambda, and then you also require some sort of almost surjectivity of the map F. So you want the map F to have a quasi-dense image in the sense that if you take any element in the target group, it will be at distance at most C from the image of F. So the distance from lambda to F of gamma is at most C. Right, so this is probably the definition of quasi-isometry that you are most familiar with. But there is another possible definition of quasi-isometry, which is an observation by Gromov, another equivalent characterization, that two finitely generated groups are quasi-isometric if and only if you can find some locally compact topological space omega on which the two groups gamma and lambda will act and you want those two actions to commute. So I really want an action of the product gamma cross lambda on omega by homeomorphisms. And, and you require that the action of gamma and omega is properly discontinuous. Meaning that if you take any compact subset of omega, there will be only finitely many elements of gamma that do not move K out of itself, and co-compact. And same for the lambda action. So you have two properly discontinuous co-compact actions of gamma and lambda on omega by homeomorphisms that commute. Okay, so I don't know if you're familiar with this characterization of quasi-isometry. It's maybe less common than this definition. Let me maybe give a proof sketch of Gromov's theorem. Okay, so first of all, let's assume that gamma and lambda are quasi-isometric. We need to construct the space omega on which they will act with this properly discontinuous co-compact actions. So what you do is you take for omega the space of all lambda c quasi-isometries from gamma to lambda. So when I say lambda c quasi-isometry, I mean something satisfying those two conditions for the constants lambda and c. This is a locally compact space. So I equip it with a pointwise convergence topology. This is a locally compact space essentially by the Arzela-Ascoli theorem, because any quasi-isometry is Lipschitz, I guess with Lipschitz constant lambda plus c. So you have a space of uniformly Lipschitz maps from gamma to lambda equipped with the pointwise convergence. It's going to be locally compact. And you have commuting actions of gamma and lambda, where the action of gamma is just by precomposition, by translation, and the action of lambda is by postcomposition, by translation. So those are the two commuting actions of gamma and lambda. I claim that they are co-compact. And why is this? It's, well, because since your quasi-isometries are C-dense, you can always, up to precomposing or postcomposing by an element, arrange that the identity of gamma is sent within a compact set of lambda. And this is exactly what you need to prove the co-compactness of the action. And it's also, they are also properly discontinuous, because essentially, if you take a compact subset K of omega, well, there will be a compact subset of lambda such that every map F in K will send F of 1 within K lambda. But then you see that you can precompose or postcompose by at most finitely many elements so that this is still satisfied. Right, so you can, because of the quasi-isometric embedding, because the distances are comparable, you can precompose by only finitely many elements so that this is still satisfied, and this gives you the proper discontinuity of the two actions. Okay, and in the other direction, assume that we have such a locally compact space. So notice here the important thing is that if I had assumed that omega was a geodesic metric space and that the actions were by isometries, the implication from here to there would just be the Schwarz-Milnor lemma, right? But what is really interesting about this theorem is that it gives you a characterization of quasi-isometry that is purely topological without any reference to any metric. In fact, be aware that the same statement with geodesic metric space is not correct. This implication is false. It's not true that if you have two groups that are quasi-isometric, you can always find a common geodesic metric space on which they act by isometries, right? So you really need to state this in the topological setting. And this is one advantage of this characterization, purely topological. Okay, so how are we going to do this? So let X be a relatively compact fundamental domain for one of those actions. I don't know, say, for example, for the action of lambda. Then you have, well, since it's a fundamental domain, every element in omega can be written as taking an element in X and applying an element of lambda, right? So you have there is a bijection between omega and X cross lambda. Yeah, I will draw it this way. I have my fundamental domain X, and I have lambda copies of X, and this is omega. Okay, now I claim that there is an action of the group gamma on X, the fundamental domain for the lambda action. And what is this action of gamma? Well, okay, so you pick a point in X, and you try to apply an element, let's call it little gamma. Well, of course, gamma is acting on omega. So when I apply gamma for the action on omega, it's going to be sent somewhere to another translate of X. But now, because this is a fundamental domain for the action of lambda, of bringing it back to X by applying an element of lambda, right? So there is a unique lambda in lambda that brings this point back to the fundamental domain X. And this is the induced action of gamma on X. And this element lambda, I will, so you have a map that compares the two actions that goes from gamma cross X to lambda, which is C of gamma X is this unique element lambda that brings me back to the fundamental domain. Okay, and I want you to notice that this map satisfies the so-called cocycle relation. That is, if you do C of gamma gamma prime, the product gamma gamma prime applied at X, you will get C of gamma applied at gamma prime X. So this gamma prime X is for this action on X, multiplied by C of gamma prime X. So I can illustrate this on my picture. Maybe let me okay, I'll draw another bigger one. Okay, so we have the point in X. I need to first apply gamma prime. I get somewhere, and then apply gamma. And I will get somewhere else. Okay. So if I apply the product gamma gamma prime, there is a unique element here that brings me back to the fundamental domain, and this element is C of gamma gamma prime. Okay, but on the other hand, so if I just apply gamma prime, there is a unique element that brings me back to the fundamental domain, And this element is C of gamma prime X, which is the one here. And now, if I start again from the point gamma prime X, this point, I apply gamma, I will get somewhere. And here, the element that brings me back is C of gamma prime, gamma dot X. Yes?
So the definition of fundamental domain is really that the translate of lambda are disjoint.
Right. Yes. And you can take one whose closure will, so that you have a unique element.
Exactly.
Yes. Okay, so right, so I have this element here, but now the thing that you should notice is that because the two actions commute, here if I do C of gamma prime X and then gamma, is the same as doing gamma and then C of gamma prime X. C of gamma prime X, yes. And then you see that this orange is the product of those two. So here I'm using the fact that the two actions commute to get the cocycle relation. Okay, now notice that if you fix an element S in gamma, which you should think of as one of the generators in the generating set, then C of Sx and C of Sy differ by the bounded amount in lambda. Because essentially, if you translate the closure of this fundamental domain by S, so you are translating a compact set, and because of the proper discontinuity of the action, the translate will mean only finitely many. You will meet only finitely many lambda translates of X when you apply S. And this is saying that the C of S little x, as X varies here, take only finitely many values. And from this and the cocycle relation, you get that C, well, if you pick any x, this function which sends gamma to C of gamma x will be Lipschitz, because, well, essentially you decompose gamma as a product in the generators, and you have a product of C of the generators applied to some element, but somehow it doesn't really depend which element you picked. So you have a Lipschitz map, and then it's not so hard to. I mean, you also need a quasi-inverse to this. So the claim is that this will be the desired quasi-isometry from gamma to lambda. And it's not so hard to see that if you imagine that X was also a fundamental domain for the action of gamma, then going the other way around gives you the quasi-inverse. In general, it's not exactly true, but both the action of gamma and the action of lambda have a compact fundamental domain, or relatively compact fundamental domain. So the union of these two is contained in the compact set, and this is enough to get the quasi-isometry. Okay, I will leave some details here, but this is roughly the idea. I guess I want to use a left invariant metric. but I hope I got it right, but I think it should be, yes. Okay, anyway, so I mentioned this theorem of Gromov because now in order to define measure equivalence, well, we will be inspired by this characterization of quasi-isometry and just do the same thing, but in a measurable setting. So the definition again is due to Gromov, and we say that two countable groups, gamma and lambda, are measure equivalent if you can find a space omega, but this time it's not going to be a topological space, it's going to be a measurable space. So this is a standard Borel set, standard measure space. Which means that, okay, it means that it's the measure space associated. So is this, so as a Borel set, is the Borel space associated to separable and completely metrizable topological space, so to Polish space, equipped with a Borel measure. But you should think that measurably omega is something like R is the Lebesgue measure, or possibly a countable set is an atomic measure, or possibly a combination of the two. Again, we have commuting actions of gamma and lambda by Borel, by measure preserving automorphisms. And now we are going to require that each of these action is, so I'm going to replace properly discontinuous by requiring the action to be free. And I'm going to replace having a compact fundamental domain by having a finite measure fundamental domain. And same for the actions. Okay, what is the main example to keep in mind? So the main example maybe to keep in mind is that if gamma and lambda are two lattices in the same ambient Lie group, or more generally in the same locally compact second countable group, then they are measure equivalent, which I will always abbreviate as N. So why is this? Because if you have a locally compact second countable group, it has a Haar measure. And the space omega will be the group G itself equipped with this Haar measure. Now, you have an action of gamma by left multiplication on G, and an action of lambda by right multiplication of G. So these are two commuting actions of gamma and lambda on G. They preserve the Haar measure. And the fact that there are lattices exactly says that they have, so they are free, and the fact that there are lattices exactly means that they both have a finite measure fundamental domain. Okay, maybe to give a very concrete example. To give a very concrete example, you can view a free group and the fundamental group of a closed surface as being lattices in the isometric group of H2, the hyperbolic plane, where, well, so this is a surface group, so this lattice here would be uniform with this as a compact quotient. And F2, if you view it as the pi1 of surface with cusps, it tells you that F2 is a non-uniform lattice in the isometric group of H. But those being lattices in the same bion group, F2 is measure equivalent to the pi1 of the surface. And here you notice a first difference between measure equivalence and quasi-isometry. For to have quasi-isometry, you would need to have uniform lattices, co-compact lattices. Here, any two lattices in the same bion group will be measure equivalent. So, right, so measure equivalent does not imply quasi-isometry, but you might think from the definition that maybe this notion is weaker than quasi-isometry, but it's not true either. So quasi-isometry does not imply measure equivalence, but this is somehow harder. But there are properties that are known to be invariant by measure equivalence, but not QI invariant. Like, for example, property T that we'll learn about this week is a measure equivalence invariant, but not a QI invariant. So you can find two finitely generated groups that are quasi-isometries, that are quasi-isometric. One has property T that doesn't, the other doesn't, and therefore they are not measure equivalent. There are other properties like that, such that ratios of L2 Betty numbers, for example, are an invariant of measure equivalent, which is not an invariant of quasi-isometry. And so none of the implications is true. Okay, maybe an even simpler example that I should say is that if gamma and lambda are finite index subgroups in the same finitely generated group G, for example, it is a special example of this. They will be measure equivalent. In general, if gamma and lambda are virtually isomorphic, which means that you can find finite index of, let me write gamma 1 and gamma 2, which means that you can find a finite index subgroup in gamma I and finite normal subgroups in gamma I naught, such that gamma 1 naught over F1 is isomorphic to gamma 2 naught over F2, something like commensurable up to finite kernels, then they are measure equivalent. This is kind of an obvious way in which groups can be measure equivalent, but the question is, can you get other behaviors? And we saw a first example, groups that are definitely not. Yes, they are. Yes, you can ask Kajal about this. He knows very much. They are both measure equivalent and quasi-isometric. Right. Yeah, I think so. So what? So you gave me the argument. It's because so product with Z. So the product of this with Z versus the universal. Yes. Yes.
Yeah. So there
Yes.
quasi-metric and also measuring.
Yeah, I think right. So the argument was that I1 of sigma plus Z is measure equivalent to F2 cross Z. And this is also a lattice. Yeah. Yeah. Right. So actually, so Kajal has a nice theorem with Romain Tessera about this, saying that so they are both measure equivalent and quasi-isometric, but you cannot have them measure equivalent with a measure equivalence cocycle that is integrable. So, okay. Maybe one thing I should mention, which is not obvious from the definition, is that measure equivalence is indeed an equivalence relation. Among countable groups. So it's clear that every group is measure equivalent to itself, just by taking the left-right multiplication on itself. It's also clear that if gamma and lambda are measure equivalent, then lambda and gamma are measure equivalent, right? So this is, you use that gamma cross lambda is isomorphic to lambda cross gamma. But the thing that is not obvious is that if gamma 1 is measure equivalent to gamma 2, and gamma 2 is measure equivalent to gamma 3, right? So you have maybe the coupling omega here and the coupling sigma there. How do you build a measure equivalence coupling between gamma 1 and gamma 3? Well, the idea is, so you have gamma 1 and gamma 2 acting on here, you have gamma 2 and gamma 3 acting on there. So you can form the product of gamma times sigma, but then you mod out by the diagonal action of gamma 2, where you act here, well, you have an action of gamma 2 here and action of gamma 2 there. So this is mod out by a diagonal action. And of course, because all those actions commute, you have an action of gamma 1 times gamma 3 on this space. And I claim that the actions will be free and with a finite measure fundamental domain. which is not very hard to see. So essentially, measurably, this is the same as doing omega times the fundamental domain for gamma 2 here. And so fundamental domain for gamma 1 will then be fundamental domain for gamma 1 times fundamental domain for gamma 2, right? And same. Okay, so this finishes the first approach to measure equivalence as an analog of quasi-isometry, and also related, as you saw, with the theory of lattices in locally compact groups. Oh, there was one last thing that I wanted to say. So in this definition that I am erasing, I will say that gamma and lambda are orbit equivalent. And we'll see right now where this terminology comes from. We say that gamma and lambda are orbit equivalent if in the definition you can take the same fundamental domain for gamma and lambda. Right, a priori, I'm asking that there are commuting actions. Each of them has a finite measure fundamental domain, but I'm not asking that the two fundamental domains coincide. I'm not even asking that the two fundamental domains have the same measure. If you can take the fundamental domains to coincide, I will say that the groups are orbit equivalent, which is a stronger notion. Okay, so this notion of orbit equivalence actually comes from ergodic theory. So now we will consider, so gamma is always countable group. And I will let X be a standard probability space. Right, so now it's 0, 1 with the Lebesgue measure, possibly with some atoms, and on which gamma acts freely preserving the measure. And let me say, I will usually want the action to be ergodic. Right, ergodic meaning that if you have a Borel subset that is gamma invariant, then it has to be null or collinear. There are no proper invariant subset for the action. Maybe I should give some examples. I don't know, you could think of the action of SLNZ on the torus, preserving the Lebesgue measure. Actually, so this is a very specific example, but all countable groups do admit such action. In fact, one thing you can do is consider what is called the Bernoulli action, where you let gamma acts on the space of maps from gamma to 0, 1, which is equipped with the probability measure. So you put Dirac mass on 0, Dirac mass on 1, and you take tensor product gamma times. And now gamma is just acting by shifting the coordinate. So this is the so-called Bernoulli action. It's not hard to check that it's indeed free and ergodic. And notice that, so I wrote 0, 1 here, but you can choose any probability space as the base, of course. Maybe another example would be if gamma is rigidly finite, then you can consider its profinite completion. It's a compact group with a Haar measure in which gamma sits as a dense subgroup. And you can look at the action by left multiplication of gamma on its profinite completion, which preserves the Haar measure. Okay, so you have plenty of examples of group actions on standard probability spaces. And I will say that two such actions, gamma acting on X, lambda acting on Y, are orbit equivalent. If essentially they have the same orbit, right? In a measurable sense, which means that if you can identify the spaces X and Y through isomorphism of measure spaces, such that for almost every X in X, this is my notation for almost every. So for almost every X in X, if you look at the gamma orbit of X, and it's identified with the lambda orbit X through this isomorphism between the two measure spaces. Okay, so we have two notions of orbit equivalence. It turns out that they are the same. So it's a theorem that's, well, maybe is already implicit in the work of Bromov, but it's really Thurman who studied this in a very detailed way, and there is also an extra argument by Gaboriau that two countable groups are orbit equivalent if and only if they admit free ergodic probability measure preserving actions on standard probability spaces. Which are orbit equivalent. This is all. And this gives a more ergodic theoretic definition of orbit equivalence. So let me give you the proof. So it will be very reminiscent of what I explained for quasi-isometry. So if you assume that the groups are orbit equivalent in the sense that there is a measure equivalence coupling between them with the same fundamental domain X. So you can view, for example, omega as being X cross lambda. And now, well, you have, as I said before, it's exactly the same as in the topological setting. You have a gamma action on X that you view as omega mod lambda, right? Where, well, you start from a point, gamma brings it somewhere, and there is a unique lambda that brings it back to the fundamental domain. And this is the action of gamma. But because the two actions have the same fundamental domain, there is also a lambda action on X when you view it as omega mod gamma, right? And because the actions commute, well, if you do gamma and lambda, it's the same as doing lambda and then gamma. And this is saying that the element lambda sends X to Y. So whenever I have an element of gamma sending X to Y, well, I also have an element of lambda sending X to Y. And this is exactly saying that those two actions have the same orbit. And we're almost done, except that those actions might fail to be free. Because it could be that the element gamma sends X here, and the element lambda brings it back to X itself. Well, the trick around this, and this is an idea that was introduced by Gaboriau, is that, well, we use another coupling. Instead of using our coupling omega, we can use the coupling omega prime, which is omega times 0,1 times the Bernoulli action of gamma, where, well, gamma and lambda, they both act on omega the same way as before. Gamma is acting here by the Bernoulli shift, and lambda is acting there trivially. And if you do this, then X cross 0,1 to the gamma is the common fundamental domain. So you can repeat the same argument as before and get orbit equivalent actions on this. But now the actions you get are free because when you apply gamma and then lambda, you have changed what happened on this coordinate. So you get free actions. And they might not be ergodic, but the thing is you can always pass to ergodic components, can always disintegrate the measure and get ergodic couplings out of any coupling to get ergodicity. Okay? So this finishes the proof of one direction, and for the other, so assume we have, let's say, gamma and lambda acting on the same space X with the same orbits, right? They are orbit equivalent up to identifying X and Y I'm assuming that they are acting on the same space with the same orbits. Then what is a measure equivalence, an orbit equivalence coupling between them? Well, essentially, you can take omega to be just the associated orbit equivalence relation. Which is, so R is the set of pairs XY where where X and Y are in the same orbits for either of the two actions. Where, for example, there exists gamma in gamma, so that Y is gamma. This is the equivalence relation, the orbits of the equivalence relation. It's the equivalence relation on the space X that gives you the orbit of any of the two actions. And now you have an action of the product on R, where, well, essentially, you let gamma act on the first coordinate and lambda act on the second. And you can check that this gives a measure equivalence coupling where the quotient actions are X on both sides. Another way of doing is to start from two actions of gamma and lambda on X. You can build an action of gamma cross lambda on X cross lambda, where lambda just shifts in the lambda direction, and gamma acts. So gamma acts on X the way it should, and there is a cocycle that gives you the action on lambda. It's the cocycle comparing the actions of gamma and lambda. Okay, I should say, so this is an ergodic characterization of orbit equivalence. There is also a similar ergodic characterization of measure equivalence, which is the following. So you say that the two actions are stably orbit equivalent. If well, maybe the orbits are not the same on the whole space, but there is a positive measure subspace where the orbits coincide. So if you can find so if you can find positive measure subsets inside X and Y, which do not need to have the same measure, and an isomorphism between, not between X and Y, but between U and V. Well, U renormalized as a probability space, V renormalized as a probability space, such that if I take almost every point in U, then the orbit of X inside of U is mapped by F. Yes, it's always 3 ergodic. Yeah. So I'm sending the orbits of x inside U to the orbit of f of x inside V. Another way of thinking of it is that if instead of renormalizing U and V, you think that you're renormalizing X and Y, it's like you have X and Y that are finite measure spaces. So you have an action of gamma on X, an action of lambda on Y that has been renormalized, and there is some common subspace on which the orbits coincide. The intersection of the orbits with that subspace coincide. Yes. Right, it's the same, but just in restriction to some positive measure subsets. So it's really right. You take some positive measure subset of X, some positive measure subset of Y, and if you to identify them, you might have to rescale the measures. But when you do this, the orbits coincide. Okay, and it's the same kind of reasoning. Yes. Right. It's just so you have an orbit relation on the whole space, and you intersect this with U. So it's the intersections of the orbits with the subset U that are the same as the intersections of the orbits with the subset. Right. I'm not saying U and V are not invariant, but like it's typically you have ergodic action. But if you just restrict the orbit to some set, you see the same orbits. Right, and now this gives a characterization of measure equivalence, that two groups are measure equivalent if and only if they have free probability method preserving ergodic SOE actions. Well, and this is really accounting for the fact that in measure equivalence, those would be the two fundamental domains for the two actions that need not have the same measure, and you cannot hope the orbits to be the same. Who knows, but you will find some positive measure where this holds.
That's the orbit and equivalence relation.
Yes.
It's that kind of a thing. Does that follow?
Yes. Right. Yes, this is true. Yes, because I mean, if you take any two Borel subsets, there will be something. Yeah. Okay, so we learned about amenability this morning. So let me give you an equivalent definition of amenability. And let's get the first important examples of groups that are measure equivalent. So this is a deep theorem due to Austin and Weiss. We are building on earlier work of Dye that all, yes, sorry. No, you mean, right, if you do the construction, it would rather be X and Y would be the fundamental domains. You can, if you think of the relation between the measure equivalence coupling, right? So if omega is the measure equivalence coupling, I guess I rather think of X and Y, the entire spaces as being fundamental domains, but you can choose them so that they have a positive measure intersection. And then if you see the thing that happens is, okay, imagine you have an action of gamma and lambda on omega, and you have two fundamental domains, and they intersect on some positive measure subset. Now, if you have an element of gamma that brings this point somewhere, and lambda brings it back to here, then you can do the same the other way around, like doing lambda and then gamma. And so on the intersection of the fundamental domain, you will see the same equivalence relation. This is the right. So if you have this situation, you can build omega where X and Y will be fundamental domains for the actions of gamma and lambda, and the orbits will, and they intersect in U. And I mean, okay, up to, right, I shouldn't say X and Y. It should be X and Y renormalized so that U and V have the same measure. So I don't know, mu of, you have to renormalize by mu of U divided by mu of V, or the other way around, I know. Okay? Okay, so Ornstein-Weiss theorem tells you that all amenable groups are measure equivalent. So from this viewpoint, this equivalence relation on groups is very weak on the class of amenable groups because it doesn't distinguish anything. And in fact, it's even stronger, is that any two pre-ergodic probability measure preserving actions of amenable groups are orbit equivalent. So not only they are measure equivalent, but they are even orbit equivalent. And it's even stronger. It's not that any two amenable groups have orbit equivalent actions, it's that any action that they will all be the same up to isomorphism. Up to, I mean, they will all be orbit equivalent. So Dai, as I mentioned, proved it for Z actions, right? So you can define an amenable group as something whose actions are orbit equivalent to an action of Z. Okay. I should say, okay, maybe let me make a few comments on this. I'm not going to prove this because one has to make choices, and I rather want to focus on measure equivalent in negative curvature. So rather proving the opposite kind of theorems where you have certain groups that are very rigid, and you get this rigidity from negative curvature. But let me still say one or two things on this. The first thing I want to mention is that so the countably infinite. All right. So this is not correct because it's not true of finite. Well, okay, I don't know. Three actions. Maybe it's correct. Okay, all countably infinite amenable groups are measure equivalent. So the countably infinite amenable groups form one class of measure equivalence among countable groups. So they're all measure equivalent, but also an amenable group is never measure equivalent to a non-amenable. This was observed by Furman using a definition of amenability in terms of some unitary representations and proving that from a measure equivalence coupling, you can, if you have a certain, if you know something about the unitary representations of gamma, then you can induce that to unitary representations of lambda, have the same kind of properties. Also, let me mention that, so we know exactly, you can describe the actions that what is the property that all these actions have in common? So what they prove is that all free ergodic EMP actions of amenable groups are hyperfinite, which means that you can find a sequence of finite subrelations such that the orbit equivalent relation associated to your actions is the union of those finite subrelations. So, right. So in fact, the action that you get can be characterized as being an increasing union of finite subrelations. And so Dai proved that all Z actions are hyperfinite, and then he proved that any two hyperfinite relations are orbit equivalent. And Orstenweis, using Fellner set, managed to extend it to amenable groups. Okay, so I should say that, so this is, the amenable case is very different from the non-amenable case. There is a theorem that's due to Epstein, and there is the long history behind it that I will tell in a second, that every non-amenable group admits a continuum of pairwise non-OE actions. Pre-ergodic probability measure preserving OE actions. So there is really a strong contrast between the two cases. In the amenable case, all actions are orbit equivalent. In the non-amenable case, for every group, you can find a continuous of pairwise non-orbit equivalent actions. So first, Gaboriau and Popa proved it for the case of the free group. Then Johanna proved that it's true for every group that contains F2. And then, in a sense, Gaboriau and Lyons proved that in a measurable sense, every non-amenable group contains a free group. In the sense that if you take a Bernoulli action of non-amenable, you can find a Bernoulli action of you have a non-amenable group, you can build the Bernoulli action of gamma, such that F2 acts on this, and the orbit equivalence relation of F2 is a sub-relation of the orbit equivalence of gamma. So in a sense, F2 measurably embeds in every non-amenable countable group, and then Epstein used this to prove this in the general case of all non-amenable groups. Okay, so I will now still have 5 minutes. Let me say a word about the measure equivalence class of the free group. So first of all, I should say that this is very mysterious. We don't understand what is the class of all groups that are measure equivalent to a free group, but we know some examples. So we saw that fundamental group of closed surfaces are measure equivalent to a free group. Gaboriau generalized this and proved that if you take certain copies of the same surface with boundary, one boundary component, and you glue them along the boundary, this gives you a group that's measure equivalent to the free group. And Brighton, Tweedale, and Wilton generalize this and prove that all elementarily free group are measure equivalent to the free group. So those that have the same elementary theory in the same sense as last week in Samstone. There is another kind of example that which is an observation of Gabarrio. That yes. It's using the work. It's using the work of Stella and knowing that essentially it's built as towers of surfaces. Yeah, right. So I mean, there are really deep things behind that. Here I'm going to state something much more elementary, that if gamma 1, so it's something about invariances of orbit equivalent, like stabilities of orbit equivalent. If you know that gamma 1 is orbit equivalent to gamma 2 and lambda 1 is orbit equivalent to lambda 2, then the free product of gamma 1 and lambda 1 will be orbit equivalent to the free product of gamma 2 and lambda 2. And so as a consequence, F2, which is the free product of Z star Z, is measure equivalent to any free product of two infinite amenable groups. So this maybe in the last 5 minutes I can explain this. Beware that it's not true if I replace orbit equivalent by measure equivalent. The simplest example being that Z mod 2Z is measure equivalent to Z mod 3Z, right? Because they are commensurable, but the free product of two copies of Z mod 2Z, which is an infinite dihedral group, which is amenable, is certainly not measure equivalent to the free product of two copies of Z mod 3Z, which is virtually free non-abelian. Yes? Yes. So the Bernoulli action, it will automatically be ergodic, the action. So you're saying about what I said here about. So the thing I was saying is you take gamma acting maybe on 0, 1 to the gamma, and you can find an action of F2 on this, whose orbits embed in the orbits of the gamma action. So somehow the equivalence relation generated by the F2 action is a sub-equivalence relation of that induced by the gamma action. It's a sort of measurable solution to the von Neumann embedding problem. I mean, it's not true that every amenable group contains non-abelian free subgroup, but somehow measurably it's true. Okay, I'm almost out of time, so maybe I'm gonna skip this. I'm gonna stop here. Maybe let me tell you what we'll do next time. So, right. So far, I've only given you examples of groups that are measure equivalent to a free group, but what are the constraints on a group to be measure equivalent to a free group? And what I will prove tomorrow is a theorem due to Adams. And it's really a place where we'll see how to exploit negative curvature to distinguish groups from the viewpoint of measure equivalence. So I prove a theorem of Adams that says essentially that if you take a free group, or more generally, a non-elementary hyperbolic group, then for example, gamma cannot split as a product of two infinite groups. And in fact, it's even better. You can prove things like, so if lambda is measure equivalent to gamma, then the centralizer of every infinite order element of lambda has to be amenable. And more generally, the normalizer of every infinite amenable subgroup of lambda will have to be amenable. Right, so in particular, a free group cannot be, a free group or a hyperbolic group cannot be measure equivalent to a direct product. And this is really a place where we'll see how negative curvature prevents this kind of big normalizers. Thank you. Mm-hmm. Yes. Yeah, I don't know. Yeah, I don't know. I don't know about this reason, but yes. Right. So, okay, if you're asking about the general thing, it's hard. Like so there is no reason that those groups would be measure equivalent. No, there are certain situations where, I mean, there are some deep theorems. For example, there is a theorem of Furman that I'll probably mention again in the third lecture, that if you take a lattice in a higher rank simple Lie group, like SL3R, then those are super rigid in measure equivalence, in the sense that if you have any countable group that is measure equivalent to this lattice, it has to be virtually isomorphic to a lattice in SL3R. So in this case, you know, you have a strong super rigidity theorem that tells you this is the whole measure equivalent class of the lattice. But in general, this is really a hard question in general. You know, it's the same complexity as classifying groups up to quasi-isometry.
Okay, great. That's nice.